5 quintillion tons, 2% of which is frozen at any given time. If Earth should ever undergo a runaway greenhouse effect like the one that has occurred on Venus, our atmosphere would trap larger amounts of solar energy, raising the air temperature and making the oceans evaporate swiftly into the atmosphere as they sustained a rolling boil. This would be bad news. Apart from the obvious ways that Earth's flora and fauna would die, an especially pressing cause of death would result from Earth's atmosphere growing 300 times more massive as it thickens with water vapor. We would be crushed and baked by the air we breathe. Our planetary fascination are hardly limited to Venus. With its long dry, still preserved meandering riverbeds, floodplains, river deltas, networks of tributaries, and river-eroded canyons, Mars must once have been a primeval Eden of water in motion. If any place in the solar system other than Earth ever boasted a flourishing water supply, it was Mars. For reasons unknown, however, today Mars has a bone-dry surface. Close examination of Venus and Mars, our sister and brother planets, forces us to look at Earth anew and to wonder how fragile our surface supply of liquid water may turn out to be. Early in the 20th century, imaginative observations of Mars by the noted American astronomer Percival Lowell led him to suppose that colonies of resourceful Martians had built an elaborate network of canals in order to redistribute water from Mars' polar ice caps to the more populated middle latitudes. To explain what he thought he saw, Lowell imagined a dying civilization that was exhausting its supply of water, like Phoenix discovering that the Colorado River has its limits. In his thorough yet curiously misguided treatise entitled Mars as the Abode of Life, published in 1909, Lowell lamented the imminent end of the Martian civilization that he imagined he saw. Indeed, Mars seems certain to dry up to the point that its surface can support no life at all. Slowly but surely, time will snuff life out, if it has not done so already. When the last living ember dies away, the planet will roll on through space as a dead world, its evolutionary career forever ended. Lowell happened to get one thing right. If Mars ever had a civilization that required water on the surface, it must have faced catastrophe, because at some unknown time in Martian history, and for some unknown reason, all the surface water did dry up, leading to the exact fate for life, though in the past, not the present, that Lowell described. What happened to the water that flowed abundantly over Mars' surface billions of years ago remains an outstanding mystery among planetary geologists. Mars does have some water ice in its polar caps, which consist mainly of frozen carbon dioxide, and a tiny amount of water vapor in its atmosphere. Although the polar caps contain the only significant amounts of water now known to exist on Mars, their total content of ice falls far below the amount needed to explain the ancient records of flowing water on Mars' surface. If most of Mars' ancient water did not evaporate into space, its most likely hiding place lies underground, with the water trapped in the planet's subsurface permafrost. The evidence? Large craters on the Martian surface are more likely than small craters to exhibit dried mud spills over their rims. If the permafrost lies deep underground, to reach it would require a large collision. The deposit of energy from such an impact would melt this subsurface ice upon contact, causing it to splash upward. Craters with this mud spill signature are more common in the cold, polar latitudes, just where we might expect the permafrost layer to be closer to the Martian surface. According to optimistic estimates of the Martian permafrost's ice content, the melting of Mars' subsurface layers would release enough water to give Mars a planet-wide ocean tens of meters deep. A thorough search for contemporary life on Mars must include a plan to search in many locations, especially below the Martian surface. So far as the chance of finding life on Mars is concerned, the great question to be resolved asks, does liquid water now exist anywhere on Mars? Part of the answer leaps from our knowledge of physics. No liquid water can exist on the Martian surface, because the atmospheric pressure there, less than 1% of the value on the surface of Earth, does not allow it. As enthusiastic mountaineers know, water vaporizes at progressively lower temperatures as the atmospheric pressure decreases. At the summit of Mount Whitney, where the air pressure falls to half of its sea level value, water boils not at 100 but at 75 degrees Celsius. On top of Mount Everest, with air pressure only a quarter of its sea level value, boiling occurs at about 50 degrees. 20 miles high, where the atmospheric pressure equals only 1% of what you feel on the sidewalks of New York, water boils at about 5 degrees Celsius. Rise a few miles higher, and liquid water will boil at 0 degrees, that is, it will vaporize as soon as you expose it to the air. Scientists use the word sublimation to describe the passage of a substance from solid to gas without any intervening liquid stage. We all know sublimation from our youth, when the ice cream man opened his magic door to reveal not only the delicacies inside but also the chunks of dry ice that kept them cold. Dry ice offers the ice cream man a great advantage over familiar water ice. It sublimates from solid to gas, leaving no messy liquid to clean up. An old detective story conundrum describes the man who hanged himself by standing on a cake of dry ice until it sublimated, leaving him suspended by a noose, and the detectives without a clue as to how he did it. What happens to carbon dioxide on Earth's surface happens to water on the surface of Mars. No chance for liquid exists there, even though the temperature on a warm day of the Martian summer rises well above 0 degrees Celsius. This seems to draw a sad veil over the prospects for life, until we realize that liquid water could exist beneath the surface. Future missions to Mars, intimately bound up with the possibility of finding ancient or even modern life on the red planet, will direct themselves toward regions where they can drill into the Martian surface in a search for the flowing elixir of life. Elixir though it may appear, water represents a deadly substance among the chemically illiterate, to be avoided sedulously. In 1997, Nathan Zahner, a 14-year-old student at Eagle Rock Junior High School in Idaho, conducted a now famous science fair experiment to test anti-technology sentiments and associated chemical phobia. Zahner invited people to sign a petition that demanded either strict control or a total ban of dihydrogen monoxide. He listed some of the odious properties of this colorless and odorless substance. It is a major component in acid rain. It eventually dissolves almost anything it comes in contact with. It can kill if accidentally inhaled. It can cause severe burns in its gaseous state. It has been found in tumors of terminal cancer patients. 43 out of 50 people approached by Zahner signed the petition, 6 were undecided, and 1 was a great supporter of the molecule and refused to sign. Yes, 86% of the passers-by voted to ban dihydrogen monoxide from the environment. Maybe that's what really happened to the water on Mars. Venus, Earth, and Mars together provide an instructive tale about the pitfalls and payoffs from focusing on water as the key to life. When astronomers considered where they might find liquid water, they originally concentrated on planets that orbit at the proper distances from their host stars to maintain water in liquid form, not too close in and not too far out. Thus we begin with the tale of Goldilocks. Once upon a time, somewhat more than 4 billion years ago, the formation of the solar system was nearly complete. Venus had formed sufficiently close to the Sun for the intense solar energy to vaporize what might have been its water supply. Mars formed so far away that its water supply became forever frozen. Only one planet, Earth, had a distance just right for water to remain a liquid, and whose surface would therefore become a haven for life. This region around the Sun where water can remain liquid came to be known as the habitable zone. Goldilocks liked things just right, too. One of the bowls of porridge in the Three Bears cottage was too hot. Another was too cold. The third was just right, so she ate it. Upstairs, one bed was too hard. Another was too soft. The third was just right, so Goldilocks slept in it. When the Three Bears came home, they discovered not only missing porridge but also Goldilocks fast asleep in their bed. The relative habitability of Venus, Earth, and Mars would intrigue Goldilocks, though the actual history of these planets is somewhat more complicated than 3 bowls of porridge. 4 billion years ago, leftover water-rich comets and mineral-rich asteroids were still pelting the planetary surfaces, although at a much lower rate than before. During this game of cosmic billiards, some planets had migrated inward from where they had formed while others were kicked into larger orbits. And among the dozens of planets that had formed, some moved on unstable orbits and crashed into the Sun or Jupiter. Others were ejected from the solar system altogether. In the end, the few planets that remained had orbits that were just right to survive billions of years. Earth settled into an orbit with an average distance of 93 million miles from the Sun. At this distance, Earth intersects a measly 1/2 billionth of the total energy radiated by the Sun. If you assume that Earth absorbs all the energy received from the Sun, then our home planet's average temperature should be about 280 Kelvin, which falls midway between winter and summer temperatures. At normal atmospheric pressures, water freezes at 273 Kelvin and boils at 373 degrees, so we are well positioned with respect to the Sun for nearly all of Earth's water to remain happily in its liquid state. Not so fast. In science you can sometimes get the right answer for the wrong reasons. Earth actually absorbs only 2/3 of the energy that reaches it from the Sun. The rest is reflected back into space by Earth's surface and by its clouds. If we factor this reflection into the equations, the average temperature for Earth drops to about 255 Kelvin, well below the freezing point of water. Something must be operating to raise our average temperature to something a little more comfortable. But wait once more. All theories of stellar evolution tell us that 4 billion years ago, when life was forming out of Earth's primordial soup, the Sun was a third less luminous than it is today, which would have left Earth's average temperature even farther below freezing. Perhaps Earth in the distant past was simply closer to the Sun. Once the early period of heavy bombardment had ended, however, no known mechanisms could have shifted stable orbits back and forth within the solar system. Perhaps the greenhouse effect from Earth's atmosphere was stronger in the past. We don't know for sure. What we do know is that habitable zones, as originally conceived, have only peripheral relevance to whether life may exist on a planet within them. This has become evident from the fact that we cannot explain Earth's history on the basis of a simple habitable zone model, and even more from the realization that water or other solvents need not depend on the heat from a star to remain liquid. Our solar system contains two good reminders that the habitable zone approach to looking for life has severe limitations. One of them lies outside the zone where the Sun can keep water liquid, yet nevertheless has a worldwide ocean of water. The other, far too cold for liquid water, offers the possibility of another liquid solvent, poison to us but potentially prime for other forms of life. Before long we should have the opportunity to investigate both of these objects with close-up robot explorers. Let's check out what we know now about Europa and Titan. Jupiter's moon Europa, which has about the same size as our moon, shows crisscrossing cracks in the surface that change on time scales of weeks or months. To expert geologists and planetary scientists, this behavior implies that Europa has a surface made almost entirely of water ice, like a giant Antarctic ice sheet girdling an entire world. And the changing appearance of the rifts and rills in this icy surface leads to a startling conclusion: the ice apparently floats on a worldwide ocean. Only by invoking liquid beneath the icy surface can scientists satisfactorily explain what they have seen, thanks to the stunning successes of the Voyager and Galileo spacecraft. Since we observe changes on the surface all around Europa, we may conclude that a worldwide ocean of liquid must underlie that surface. What liquid could this be, and why should that substance remain liquid? Impressively, planetary scientists have reached two fairly firm additional conclusions. The liquid is water, and it remains liquid because of tidal effects on Europa produced by the giant planet Jupiter. The fact that water molecules are more abundant than ammonia, ethane, or methyl alcohol makes it the likeliest substance to provide the liquid beneath Europa's ice, and the existence of this frozen water likewise implies that more water exists in the immediate neighborhood. But how can water remain a liquid when the solar-induced temperatures in Jupiter's vicinity are only about 120 K? Europa's interior remains relatively warm because tidal forces from Jupiter and the two large moons nearby, Io and Ganymede, continuously flex the rocks within Europa as this moon changes its position with respect to neighboring objects. At all times, the sides of Io and Europa closest to Jupiter feel a stronger force of gravity from the giant planet than the sides farthest away. These differences in force slightly elongate the solid moons in the direction facing Jupiter. But as the moon's distances from Jupiter change during their orbits, Jupiter's tidal effect, the difference in force exerted on the near side and the far side also changes, producing small pulses in their already distorted shapes. This changing distortion heats the moon's interiors. Like a squash ball or a racquetball continually being smashed by impact, any system that undergoes continuing structural stress will have its internal temperature rise. With a distance from the sun that would otherwise guarantee a forever frozen ice world, Io's stress level earns it the title of the most geologically active place in the entire solar system, complete with belching volcanoes, surface fissures, and plate tectonics. Some have analogized modern-day Io to the early Earth, when our planet was still piping hot from its episode of formation. Inside Io, the temperature rises to the point that volcanoes continually blast evil-smelling compounds of sulfur and sodium many miles above the satellite's surface. Io in fact has too high a temperature for liquid water to survive, but Europa, which undergoes less tidal flexing than Io because it is farther from Jupiter, heats more modestly, though still significantly. In addition, Europa's worldwide ice cap puts a pressure lid on the liquid below, preventing the water from evaporating and allowing it to exist for billions of years without freezing. So far as we can tell, Europa was born with its water, ocean and ice above, and has maintained that ocean, close to the freezing point but still above it, through 4.5 billion years of cosmic history. Astrobiologists therefore view Europa's worldwide ocean as a prime target for investigation. No one knows the ice cap's thickness, which might range from a few dozen yards to half a mile or more. Given the fecundity of life within Earth's oceans, Europa remains the most tantalizing place in the solar system to search for life outside of Earth. Imagine going ice fishing there. Indeed, engineers and scientists at the Jet Propulsion Laboratory in California have begun to envision a space probe that lands, finds a hole in the ice, and drops a submersible camera to have a peek at primitive life that may swim or crawl below. Primitive pretty much sums up our expectations, because any would-be forms of life would have only small amounts of energy at their disposal. Nevertheless, the discovery of enormous masses of organisms at depths a mile or more beneath the basalts of Washington state, living mainly on geothermal heat, suggests that we may someday find the European oceans alive with organisms unlike any on Earth. But one pressing question remains: would we call the creatures Europans or Europeans? Mars and Europa offer targets numbers 1 and 2 in the search for extraterrestrial life within the solar system. A third great search-me sign appears twice as far from the Sun as Jupiter and its moons. Saturn has one giant moon, Titan, which ties with Jupiter's champion, Ganymede, as the largest moon in the solar system. Half again as large as our own moon, Titan possesses a thick atmosphere, a quality unequaled by any other moon. Unlike the atmospheres of Mars and Venus, Titan's atmosphere, many dozen times thicker than Mars, consists primarily of nitrogen molecules, just as Earth's does. Floating within this transparent nitrogen gas are enormous numbers of aerosol particles, a permanent Titanian smog, that forever shrouds the moon's surface from our gaze. As a result, speculation about life's possibilities has enjoyed a field day on Titan. We have measured the moon's temperature by bouncing radio waves, which penetrate the atmospheric gases and aerosols from its surface. Titan's surface temperature, close to 85.0 Kelvin, falls far below those that allow liquid water to exist, but provides just the right temperature for liquid ethane, a carbon-hydrogen compound familiar to those who refine petroleum products. For decades, astrobiologists have imagined ethane lakes on Titan, chock full of organisms that float, eat, meet, and reproduce. Now, during the first decade of the 21st century, exploration has finally replaced speculation. The Cassini-Huygens mission to Saturn, a collaboration of NASA with the European Space Agency, left Earth in October 1997. Nearly 7 years later, having received gravity boosts from Venus, Earth, and Jupiter, the spacecraft reached the Saturn system, where it fired its rockets to achieve an orbit around the ringed planet. The scientists who designed the mission arranged for the Huygens probe to detach itself from the Cassini spacecraft late in 2004, to make the first descent through Titan's satellite's opaque clouds, and to reach the moon's surface. using a heat shield to avoid frictional burning from its rapid passage through the upper atmosphere and a series of parachutes to slow the probe down in the lower atmosphere. 6 instruments aboard the Huygens probe were built to measure the temperature, density, and chemical composition of Titan's atmosphere, and to send images back to Earth via the Cassini spacecraft. At this time, we can only await these data and images to see what they tell us about the enigma that lies beneath the clouds of Titan. We are unlikely to see life itself, should any exist on this faraway moon, but we can expect to determine whether or not conditions do favor the existence of life by providing liquid pools and ponds in which life might originate and flourish. At the very least, we may expect to learn the array of different types of molecules that exist on and near the surface of Titan, which may shed new light on how the precursors of life arose on Earth and throughout the solar system. If we require water for life, must we restrict ourselves to planets and their moons, on whose solid surfaces water can accumulate in quantity? Not at all. Water molecules, along with several other household chemicals such as ammonia and methane and ethyl alcohol, appear routinely in cool interstellar gas clouds. Under special conditions of low temperature and high density, an ensemble of water molecules can be induced to transform and to funnel energy from a nearby star into an amplified, high-intensity beam of microwaves. The atomic physics of this phenomenon resembles what a laser does with visible light. But in this case, the relevant acronym is MASER, for microwave amplification by the stimulated emission of radiation. Not only does water occur practically everywhere in the galaxy, but it also occasionally beams at you as well. The great problem faced by would-be life in interstellar clouds arises not from a lack of raw materials but from the extremely low densities of matter, which enormously reduce the rate at which particles collide and interact. If life takes millions of years to arise on a planet such as Earth, it might take trillions of years to do so at much lower densities, far more time than the universe has so far provided. By completing our search for life in the solar system, we might seem to have finished our tour through the fundamental questions linked to our cosmic origins. We cannot, however, leave this arena without a look at the great origin issue that lies in the future, the origin of our contact with other civilizations. No astronomical topic grips the public imagination more vividly, and none offers a better chance to draw together the strands of what we have learned about the universe. Now that we know something about how life might begin on other worlds, let's examine the chances of satisfying a human desire as deep as any, the wish to find other beings in the cosmos with whom we might talk things over. Searching for life in the Milky Way galaxy. We have seen that within our own solar system, Mars, Europa, and Titan offer the best hopes for discovering extraterrestrial life, either alive or in fossil form. These 3 objects present by far the best chances for finding water or another substance capable of providing a liquid solvent within which molecules can meet to carry on life's work. Because only these 3 objects seem likely to have pools or ponds, most astrobiologists limit their hopes of finding life in the solar system to the discovery of primitive forms of life on one or more of them. Pessimists have a reasonable argument, someday to be upheld or refuted by actual exploration, that even though we may well find conditions suitable for life on one or more of this favored threesome, life itself may well prove entirely absent. Either way, the results of our searches on Mars, Europa, and Titan will be laden with significance in judging the prevalence of life in the cosmos. Optimists and pessimists already agree on one conclusion: if we hope to find advanced forms of life that consists of creatures larger than the simple, single-celled organisms that appeared first and remain dominant in Earth life, then we must look far beyond the solar system, to planets that orbit stars other than the Sun. Once upon a time, we could only speculate about the existence of these planets. Now that well over 100 exosolar planets have been found, basically similar to Jupiter and Saturn, we may confidently predict that only time and more precise observations separate us from the discovery of Earth-like planets. The final years of the 20th century seem likely to mark the moment in history when we acquired real evidence for an abundance of habitable worlds throughout the cosmos. Thus the first 2 terms in the Drake equation, which together measure the numbers of planets orbiting stars that last for billions of years, now imply high rather than low values. The next 2 terms, however, which described the probability of finding planets suitable for life, and of life actually springing into existence on such planets, remain nearly as uncertain as they did before the discovery of exosolar planets. Even so, our attempts to estimate these probabilities seem to rest on firmer grounds than our numbers for the final two terms, the probability that life on another world will evolve to produce an intelligent civilization, and the ratio of the average amount of time that such a civilization will survive to the lifetime of the Milky Way galaxy. For the first 5 terms in the Drake equation, we can offer our planetary system and ourselves as a representative example, though we must always invoke the Copernican principle to avoid measuring the cosmos against ourselves, rather than the reverse. When we get to the equation's final term, however, an attempt to estimate the average lifetime of a civilization once it has acquired the technological capacity to send signals across interstellar distances, we fail to reach an answer even if we take Earth as a guide, since we have yet to determine how long our own civilization will last. We have now possessed interstellar signaling capacity for nearly a century, ever since powerful radio transmitters began to send messages across Earth's oceans. Whether we last as a civilization for the next century, through the next millennium, or throughout 1,000 centuries depends on factors far beyond our capacity to foresee, though many of the signs seem unfavorable to our long-term survival. Asking whether our own fate corresponds to the average in the Milky Way takes us into another dimension of speculation, so the final term in the Drake equation, which affects the result as directly as all the others, may be judged just plain unknown. If, in an optimistic assessment, most planetary systems contain at least one object suitable for life, and if life originates on a sensibly high fraction of those suitable objects, and if intelligent civilizations likewise appear on, perhaps, 1/10 of the objects with life, then at some point in the history of the Milky Way's 100 billion stars, 1 billion locations could produce an intelligent civilization. This enormous number springs, of course, from the fact that our galaxy contains so many stars, most of them much like our Sun. For a pessimistic view of the situation, simply change each the numbers to which we assign values from 1/10 to 1 chance in 10,000. Then the billion locations become 1,000, lower by a factor of 1 million. This makes a major difference. Suppose that an average civilization, qualifying as a civilization by possessing interstellar communications ability, lasts for 10,000 years, approximately 1 part in a million of the Milky Way's lifetime. On the optimistic view, a billion places give birth to a civilization at some point in history, so at any representative time, about 1,000 civilizations should be flourishing. The pessimistic view, in contrast, implies that in each representative era about 0.001 civilization should exist, making ourselves a lone and lonely blip that temporarily rises high above the average value. Which estimate has the greater chance of coming close to the true value? In science, nothing convinces so well as experimental evidence. If we hope to determine the average number of civilizations in the Milky Way, the best scientific approach would measure how many civilizations now exist. The most direct way to perform that feat would survey the entire galaxy, as the cast of television Star Trek love to do, noting the number and type of each civilization that we encounter, if indeed we find any. Unfortunately, this survey lies far outside our current technological capability and budgetary constraints. Besides, surveying the entire galaxy would take millions of years, if not longer. Consider what a television program about interstellar space surveys would be like if it limited itself by what we know of physical reality. A typical hour would show the crew complaining and bickering, aware that they had come so far yet still had so far to go. "We've read all the magazines," one of them might remark. "We're sick of each other, and you, Captain, are a great pain in the plethora." Then, while other crew members sang songs to themselves and still others entered private worlds of madness, a trailing long shot would remind us that the distances to other stars in the Milky Way are millions of times greater than the distances to other planets in the solar system. Their light takes many years to reach us. A full tour of the Milky Way would take us nearly 10,000 times farther. Hollywood films depicting interstellar space flight deal with this all-important issue by ignoring it, assuming that better rockets or improved understanding of physics will deal with it. or offering intriguing approaches such as freeze-drying astronauts so that they can survive immensely long journeys. All of these approaches have a certain appeal, and some offer creative possibilities. We may indeed improve our rockets, which can now reach speeds of only about 1/10,000th of the speed of light, the fastest we can hope to travel according to our current knowledge of physics. Even at the speed of light, however, travel to the nearest stars will take many years, and travel across the Milky Way close to 1,000 centuries. Freeze-drying astronauts has some promise, but so long as those on Earth, who presumably will pay for the trip and remain unfrozen, the long passages of time before the astronauts return argues against easy funding. Given our short attention spans, by far the better approach to establishing contact with extraterrestrial civilizations, provided that they exist, appears right here on Earth. All we need do is to wait for them to contact us. This costs far less and can offer the immediate rewards that our society so eagerly craves. Only one difficulty arises: why should they? Just what about our planet makes us special to the point that we merit attention from extraterrestrial societies, assuming that they exist? On this point more than any other, humans have consistently violated the Copernican principle. Ask anyone why Earth deserves scrutiny, and you are likely to receive a sharp, angry stare. Almost all conceptions of alien visitors to Earth, as well as a sizable part of religious dogma, rest on the unspoken. Obvious conclusion that our planet and our species rank so high on the list of universal marvels that no argument is needed to support the astronomically strange contention that our speck of dust, nearly lost in its Milky Way suburb, somehow stands out like a galactic beacon. Not only demanding but also receiving attention on a cosmic scale. This conclusion springs from the fact that the actual situation appears reversed when we view the cosmos from Earth. Then planetary matters bulk large, while the stars seem tiny points of light. From a quotidian point of view, this makes complete sense. Our success at survival and reproduction, like that of every other organism, has little to do with the cosmos that surrounds us. Among all astronomical objects, only the sun, and to a much lesser extent the moon, affect our lives, and their motions repeat with such regularity that they almost seem part of the earthbound scene. Our human consciousness, formed on Earth from countless encounters with terrestrial creatures and events, understandably renders the extraterrestrial scene as a far distant backdrop to the important action at center stage. Our error lies in assuming that the backdrop likewise regards ourselves as the center of activity. Because each of us adopted this erroneous attitude long before our conscious minds attained any dominion or control over our patterns of thinking, we cannot eliminate it entirely from our approach to the cosmos even when we choose to do so. Those who impose the Copernican principle must remain ever vigilant against the murmurings of our reptilian brains, assuring us that we occupy the center of the universe, which naturally directs its attention our way. Human thought, as omnipresent and self-deceiving as our anti-Copernican prejudices. Human beings trust their memories far more than reality can justify. We do so for the same survival value reasons that we regard Earth as the center of the cosmos. Memories record what we perceive, and we do well to pay attention to this record if we seek to draw conclusions for the future. Now that we have better means of recording the past, however, we know better than to rely on individual memories for all matters of importance to society. We transcribe congressional debates and laws in print, videotape crime scenes, and make surreptitious audio recordings of criminal activity, because we recognize these media as superior to our own brains for creating a permanent record of past events. One great apparent exception to this rule remains. We continue to accept eyewitness testimony as accurate, or at least probative, in legal proceedings. We do so despite test after test that demonstrates that each of us, despite our best intentions, will fail to remember events accurately, especially when those memories, as they usually do in cases important enough to go to trial, deal with unusual and exciting occurrences. Our legal system accepts eyewitness testimony from long tradition, because of its emotional resonance, and most of all because it often provides the only direct evidence of past events. Nevertheless, every courtroom cry of, "That's the man who held the pistol," must be weighed against the many demonstrated cases where that was not the man, despite the witness's sincere belief to the contrary. If we bear these facts in mind and we analyze reports of unidentified flying objects, we can immediately recognize an enormous potential for error. By definition, UFOs are bizarre occurrences, which cause observers to discriminate among familiar and unfamiliar objects on the rarely examined celestial backdrop, and typically require rapid conclusions about these objects before they quickly disappear. Add to this the psychic charge arising from the observer's belief in having witnessed a tremendously unusual event, and we could hardly find a better textbook example of a situation likely to generate an erroneous memory. What can we do to obtain data on UFO reports more reliable than eyewitness accounts? In the 1950s, astrophysicist J. Allen Hynek, then a leading Air Force consultant on UFOs, liked to highlight this issue by whipping a miniature camera from his pocket, insisting that if he ever saw a UFO, he would use the camera to obtain valid scientific evidence, because he knew that eyewitness testimony would not qualify. Unfortunately, improvements in technology since that time allow the creation of fake images and video recordings barely distinguishable from honest ones, so that Hynek's plan would no longer allow us to put our faith in photographic evidence supporting a UFO sighting. In fact, when we consider the interaction of memory's fragile power with the inventiveness of human con artists, we cannot easily devise a test to discriminate between fact and fancy for any individual UFO sighting. When we turn to the more modern phenomenon of UFO abductions, the ability of the human psyche to trump reality becomes even more apparent. Although hard numbers cannot be easily obtained, in recent years tens of thousands of people have apparently come to believe that they have been taken aboard an alien spacecraft and subjected to examinations, often of the most humiliating variety. From a calm perspective, stating this claim suffices to refute it as reality. Direct application of the principle of Occam's razor, which calls for the simplest explanation that fits the alleged facts, leads to the conclusion that these abductions have been imagined, not undergone. Because nearly all of the retellings place the abduction deep in the nighttime, and the majority in the midst of sleep, the likeliest explanation involves the hypnagogic state, the boundary between sleep and waking. For many people, this state brings visual and auditory hallucinations, and sometimes a waking dream, in which the person feels conscious but unable to move. These effects pass through the filters of our brains to yield seemingly real memories, capable of arousing unshakable belief in their certainty. Compare this explanation of UFO abductions with an alternative, that extraterrestrial visitors have singled out Earth and arrived in sufficient numbers to abduct humans by the thousands, though only briefly, and apparently to examine them closely. Some stories imply that aliens extract some useful substances from their abductees, or plant their seeds into female victims, or alter their mind patterns to avoid later detection. These assertions cannot be dismissed categorically, any more than we can rule out the possibility that alien visitors wrote these words, attempting to lull human readers into a false sense of security that will further the aliens' plans for world or cosmic domination. Instead, relying upon our ability to analyze situations rationally, and to discriminate between more likely and less likely explanations, we can assign an extremely low probability to the abduction hypothesis. One conclusion seems unassailable by UFO skeptics and believers alike. If extraterrestrial societies do visit Earth, they must know that we have created worldwide capabilities for disseminating information and entertainment, if not for distinguishing one from the other. To say that these facilities would be open to any alien visitors caring to use them amounts to a gross understatement. They would receive immediate permission, and could make their presence felt in a minute, if they cared to. The absence of apparent extraterrestrials from our television screens testifies either to their absence from Earth or to their unwillingness to reveal themselves to our gaze, the shyness problem. The second explanation raises an intriguing conundrum. If alien visitors to Earth choose not to be detected, and if they possess technology far superior to ours, as their journeys across interstellar distances imply, why can they simply not succeed in their plans? Why should we expect to have any evidence, visual sightings, crop circles, pyramids built by ancient astronauts, memories of abductions, if the aliens prefer that we don't? They must be messing with our minds, enjoying their little game of cat and mouse. Quite probably they are secretly manipulating our leaders too, a conclusion that snaps much of politics and entertainment into immediate focus. The UFO phenomenon highlights an important aspect of our consciousness. Believing though we do that our planet forms the center of creation, and that our starry surroundings must decorate our world, rather than the reverse, we nevertheless maintain a strong desire to connect with the cosmos. Manifested in mental activities as disparate as credence in extraterrestrial visitor reports and belief in a benevolent deity that sends thunderbolts and emissaries to Earth. The roots of this attitude lie in the days when a self-evident distinction existed between the sky above and Earth below, between the objects we could touch and scratch and those that moved and shone but remained forever beyond our reach. From these differences we drew distinctions between the earthly body and the cosmic soul, the mundane and the marvelous, the natural and supernatural. The need for a mental bridge connecting these two apparent aspects of reality has informed many of our attempts to create a coherent picture of our existence. Modern science's demonstration that we are stardust has thrown an enormous wrench into our mental equipment, from which we are still struggling to recover. UFOs suggest new messengers from the other part of existence, all-powerful visitors who well know what they are up to while we remain ignorant, barely aware that the truth is out there. This attitude was captured well in the classic film The Day the Earth Stood Still, in which an alien visitor, far wiser than we, comes to Earth to warn that our violent behavior may lead to our own destruction. Our innate feelings about the cosmos manifest a dark side that projects our feelings about human strangers onto non-human visitors. Many a UFO report contains phrases similar to, "I heard something odd outside, so I took my rifle and went to see what it was." Films that depict aliens on Earth likewise slip easily into a hostile mode, from the Cold War epic Earth versus the Flying Saucers, in which the military blasts away at alien spacecraft without pausing to ask their intentions, to Signs, in which the peace-loving hero, with no rifle at hand, uses a baseball bat to chastise his trespassers, a method not likely to succeed against actual aliens capable of crossing interstellar distances. The greatest arguments against interpreting UFO reports as evidence for extraterrestrial visitors reside in our planet's unimportance, together with the vast distances between the stars. Neither can be regarded as absolute bars to this interpretation, but in tandem they form a powerful argument. Must we, then, conclude that because Earth lacks popular appeal, our hopes of finding other civilizations must await the day when we can expend our own resources to embark on journeys to other planetary systems? Not at all. The scientific approach to establishing contact with other civilizations within the Milky Way and beyond, should they exist, has always relied on letting nature work in our favor. This principle redirects the question, what aspect of extraterrestrial civilizations would we find most exciting? Into the scientifically fruitful one, what seems to be the most likely means of establishing contact with other civilizations? Nature. And the immense distances between stars supply the answer. Use the cheapest, fastest means of communication available, which presumably holds the same rank elsewhere in the galaxy. The cheapest and fastest way to send messages between the stars uses electromagnetic radiation, the same medium that carries almost all long-range communication on Earth. Radio waves have revolutionized human society by allowing us to send words and pictures around the world at 186,000 miles per second. These messages travel so rapidly that even if we beam them up to a stationary satellite orbiting at an altitude of 23,000 miles, which relays them to another part of Earth's surface, they undergo a time delay on each leg of their journey much shorter than 1 second. Over interstellar distances, the time lag grows longer, though it remains the shortest we can hope to achieve. If we plan to send a radio message to Alpha Centauri, the star system closest to the Sun, we must plan on a travel time of 4 years in each direction. Messages that travel for, say, 20 years can reach several hundred stars, or any planets that orbit them. Thus, if we are prepared to wait for a round trip of 40 years, we could beam a message toward each of these stars, and eventually find out whether we receive a reply from any of them. This approach assumes, of course, that if civilizations exist close to any of these stars, they have a command of radio, and an interest in it. The fundamental reason why we don't adopt this approach in searching for other civilizations lies not in its assumptions but in our attitudes. 40 years is a long time to wait for something that may never happen. The only serious attempt in this direction occurred in the 1970s, when astronomers celebrated the upgrading of the radio telescope near Arecibo, Puerto Rico, by using it to beam a message for a few minutes in the direction of the star cluster M13. Since the cluster lies 25,000 light-years away, any return message will be a long time coming, rendering the exercise more a demonstration than an actual casting call. In case you think that discretion has inhibited our broadcasting, recall that all of our post-World War II radio and television broadcasting, as well as our powerful radar beams, have sent spherical shells of radio waves into space. Expanding at the speed of light, the messages from the Honeymooners and I Love Lucy era have already washed over thousands of stars, while Hawaii Five-0 and Charlie's Angels have reached hundreds. If other civilizations really could disentangle individual programs from the cacophony of Earth's radio emission, now comparable to or stronger than that from any solar system object, including the Sun, there might be some truth to the playful speculation that the content of these programs explains why we have heard nothing from our neighbors, because they find our programming either so appalling or so overwhelmingly impressive that they choose not to reply. A message might arrive tomorrow, laden with intriguing information and commentary. Herein lies the greatest appeal of communication by electromagnetic radiation. Not only is it cheap, it is also instantaneous, provided that we can receive and interpret another civilization's emission. This also provides a fundamental aspect of UFO excitement, but in this case we might actually receive transmissions that could be recorded, verified as real, and studied for as long as it would take to understand them. In the search for extraterrestrial intelligence, shortened to SETI by the scientists who engage in it, the focus remains on searching for radio signals, though the alternative of looking for signals sent with light waves should not be rejected. Although light waves from another civilization must compete with myriad natural sources of light, laser beams offer the opportunity to concentrate the light into a single color or frequency, the same approach that allows radio waves to carry messages from different radio or television stations. So far as radio waves go, our hopes for success in SETI rest with antennas that can survey the sky, receivers that record what the antennas detect, and powerful computers that analyze the receiver's signals in a search for the unnatural. Two basic possibilities exist. We might find another civilization by eavesdropping on its own communications, some of which leaks into space in the same way that our radio and television broadcasts do, or we might discover deliberately beamed signals meant to attract the attention of previously uncatalogued civilizations such as our own. Eavesdropping clearly presents a more difficult task. A beamed signal concentrates its power in a particular direction, so that detecting that signal becomes much easier if it should be deliberately sent toward us, whereas signals that leak into space diffuse their power more or less evenly in all directions and are therefore much weaker at a particular distance from their source than a beamed signal. Furthermore, a beamed signal would presumably contain some easy warm-up exercises to tell its recipients how to interpret it, whereas radiation that leaks into space presumably carries no such user's manual. Our own civilization has leaked signals for many decades, and has sent a beamed signal in one particular direction for a few minutes. If civilizations are rare, any attempts to find them ought to concentrate on eavesdropping and avoid the lure of hoping for deliberately beamed signals. With ever better systems of antennas and receivers, SETI proponents have begun to eavesdrop on the cosmos, hoping to find evidence for other civilizations. Precisely because we have no guarantee that we shall ever hear anything by eavesdropping, those who engage in these activities have had difficulty securing funding. In the early 1990s, the U.S. Congress supported a SETI program for a year, until cooler heads pulled the plug. SETI scientists now draw their supports, in part, from millions of people who download a screensaver from the website that co-ops home computers to analyze data for alien signals in their spare time. Even more funding has come from wealthy individuals, most notably the late Bernard Oliver, a prominent Hewlett-Packard engineer with a lifelong interest in SETI, and Paul Allen, the co-founder of Microsoft. Oliver spent many years thinking about the basic problem in SETI, the difficulty of searching through billions of possible frequencies at which other civilizations might be broadcasting. We divide the radio spectrum into relatively wide bands, so that only a few hundred different frequencies exist for radio and television broadcasts. In principle, however, alien signals might be confined so narrowly in frequency that the SETI dial would need billions of entries. Powerful computer systems, which lie at the heart of current SETI efforts, can meet this challenge by analyzing hundreds of millions of frequencies simultaneously. On the other hand, they have not yet found anything suggestive of another civilization's radio communications. More than 50 years ago, the Italian genius Enrico Fermi, perhaps the last great physicist to work both as an experimentalist and as a theorist, discussed extraterrestrial life during lunch with his colleagues. Agreeing that nothing particularly special distinguishes Earth as an abode for life, the scientists reached the conclusion that life ought to be abundant in the Milky Way. In that case, Fermi asked, in a query that ripples across the decades, where are they? Fermi meant that if many places in our galaxy have seen the advent of technologically advanced civilizations, surely we should have heard from one of them by now, by radio or laser messages if not by actual visits. Even if most civilizations die out quickly, as ours may, the existence of large numbers of civilizations implies that some of them should have sufficiently extended lifetimes to mount long-term searches for others. Even if some of these long-lived civilizations do not care to engage in such searches, others will. So the fact that we have no scientifically verified visits to Earth, nor reliable demonstrations of signals produced by another civilization, may prove that we have badly overestimated the likelihood that intelligent civilizations arise in the Milky Way. Fermi had a point. Every day that passes adds a bit more evidence that we may be alone in our galaxy. However, when we examine the actual numbers, the evidence looks weak. If several thousand civilizations exist in the galaxy at any representative time, the average separation between neighboring civilizations will be a few thousand light years, 1,000 times the distance to the closest stars. If one or more of these civilizations has lasted for millions of years, we might expect that by now they should have sent us a signal, or revealed themselves to our modest eavesdropping efforts. If, however, no civilization attains anything like this age, then we shall have to work harder to find our neighbors, because none of them may be engaged in a galaxy-wide attempt to find others, and none of them may be broadcasting so powerfully that our present eavesdropping efforts can find them. Thus we remain in a familiar human condition, poised at the edge of events that may not occur. The most important news in human history could arrive tomorrow, next year, or never. Let us go forth into a new dawn, ready to embrace the cosmos as it surrounds us, and as it reveals itself, shining with energy and replete with mystery.